Today, we're going to be covering electron configurations. So let's start off by answering what is an electron configuration. So basically, an electron configuration is a representation of the distribution of electrons within an atom's orbitals. And if we're going to talk about electron configurations, we first have to understand shells, subshells, and orbitals. And every atom has at least one shell in which electrons can move around in. And some atoms only have one shell, like hydrogen. And others, like krypton, have more. And we're going to cover how to determine the number of shells an element has later on. But for now, let's look at this diagram that shows the organization of the three topics we're covering. And as you can see, the subshells are within a shell. So that means a subshell is basically a subdivision of a shell, and orbitals are subdivisions of subshells. Now, there are four types of subshells. There are the S subshells, the P subshells, the D subshells, and the F subshells. And a subshell is organized into one of these groups based on how electrons move in the subshell. As you can see in the P subshell, there is this kind of hourglass or infinity shape, and that determines how electrons can move around. And that's different from the S subshell, which has a sphere. So that's the basic way they group them into which subshell it is. Now, we're going to focus on the S subshell for now. The S subshell is the shell with the lowest energy level. And an S subshell, you can see, has basically one orbital that looks like a sphere. And this is unlike the P subshell, which has three orbitals. Now, every orbital can have 2 electrons, as you can see in this diagram. And since the S subshell only has one orbital, it means that the S subshell in total can have only 2 electrons. That's the maximum number it can hold. Now, the P subshells have 3 orbitals. And you can see the hourglass shape here, or infinity. And since it has 3 orbitals, it means that the P subshell, the P subshell can have a total of 6 electrons. And every element after helium has a P subshell. Now, the D subshell. The D subshell has 5 orbitals. And that means that the D subshell can have a total of 10 electrons. And you can see that the subshells look kind of weird, especially the one in the middle. But we don't have to know the specific information on how these subshells look and everything. It doesn't matter right now. So every element after neon has a D subshell. And that's pretty much it for the D subshell for now. And now we have the F subshell. The F subshell has the most orbitals, 7 orbitals, as you can see there. And that means that the F subshell can have a total of 14 electrons. 2 times 7. And every element after argon has an F subshell. Now that we've talked about the subshells and the different types and how they're categorized, their differences, all that, we're going to talk about the energy levels now. So basically, energy levels are just the shells. So you can see in this diagram, E1, energy level 1, is the first shell. E2 is the second shell, E3 is the third shell, and E4 is the fourth shell. Now, these are shells, not subshells, because within each shell we have the subshells, as I've said before. And the subshells are also organized based on their energy, just like the shells. And this takes us to the Aufbau Principle, which states that electrons fill up atomic orbitals with the lowest energy level before occupying orbitals of higher energy levels. And what this basically means is that electrons aren't going to fill up in the E1 shell first, then the E2 shell, then the E3, and then the E4. And when it fills up the E shell first, E1 shell, it's going to fill up its S subshell first. And actually, that's the only subshell that the first shell has. But now it's going to fill up the 2 shell after that, and the 2 shell has 2 subshells, the S and the P subshells. And the S subshell, as I mentioned before, is at a lower energy level, so it's going to fill up the S subshell first, and then the P. Then we're going to move on to the 3rd energy level, or shell. We're just going to fill up the S, P, and then the D. Then the 4th, again, S, P, D, and F. But you can see that there's some overlap here in energy level between the different shells. And basically, when we write our electron configurations, the 4s orbital is going to come before the 3d orbitals. But don't worry about that now. Just know that electrons fill up the lowest energy level orbitals first, and then the higher ones. Now we're actually going to get into determining the electron configurations. And the easy way to do this is by looking at the periodic table, because you don't have to look at the energy diagram and where every electron goes like that. So with the periodic table, which we have here, you can easily determine the electron configurations. And here we have a helium, and we're going to move it over to the left with the hydrogen just to make things more understandable. So let's start off with explaining the periods in the periodic table. So every element in the first period has 1 shell. Every element in the second period has 2 shells. And then every element in the 3rd, 4th, 5th, 6th, 7th period, they have corresponding number of shells based on which period they are. So 3s3, 4s4, 5s5, 6s6, 7s7. And this also helps to account for the trend that atoms have a larger radius as you go down the table of elements, because you have a whole additional shell or layer of electrons to move around in. Now we're going to talk about the columns and your groups. Your groups help determine which shells are being filled. Your first 2 columns belong to the S subshell block, and then the 10 columns after that, they're dedicated to the transition metals. And then you have your P block, which is the other 6 columns over here. Then finally you have your F block, which are these lanthanides and actinides. And if you pay attention, you'd notice that the number of columns for each subshell block also corresponds with the number of electrons each subshell can hold. So the S has 2 columns, so it can hold 2 electrons. The D has 10, it can hold 10 electrons, P can hold 6, and the F can hold 14. Okay, and now we're gonna give some examples later on. But with the Aufbau Principle, we would begin filling up shells. With the very top left, because that's the one with the lowest energy level. And we'd work our way across the period to the right until we get to the end, and then we go down to the next layer. And again, go to the right, down, and go to the right. And if that sounds confusing, we're going to give some examples right now in order to get a better understanding. Okay, so the first electron configuration we're going to do is for hydrogen. And its electron configuration is just 1s1. And this notation tells us 3 things. Number tells us the energy level, or the shell. And as you can see, hydrogen is in period 1, so the 1 is here. And then the letter shows us the subshell. And you can see that hydrogen has an S subshell because it's in the first group. And then finally, the superscript shows us the number of electrons within the subshell. And hydrogen only has 1 electron, so that's why we only have a 1. Next up, let's do the second element on the table, helium. As always, we're going to start from the top left and work our way over, adding an electron every time we go across the table of elements. And since we're starting in the first period, our coefficient would be 1. And since helium lies in the same S block, we still have an S right next to our number. Our superscript this time is going to be different. It's going to be 2 this time. It's because neutral helium has 2 electrons. And we mentioned earlier that an S shell has only 1 orbit, meaning it can hold 2 electrons. So that means that this notation tells us that this subshell is completely filled with 2 electrons. And this leads to the highest level of stability, which is one of the main reasons why helium is considered a noble gas, because its subshell is completely filled. Next, we go to lithium, and you might be tempted just to say, oh, it's in the second period within the first column, so its electron configuration should just be 2s1. But this isn't the case, because you see we only have 1 electron. So where did the other 2 go? Well, we forgot about the Aufbau Principle. And remember, according to Aufbau Principle, we have to first fill up the S subshell in the first period. So that's why we add a 1s2. So this subshell is full, so it moves on to the next energy level. And if you remember, every element after helium has a p subshell. But looking at the p subshell of lithium, you see that it has no electrons. So it's 2p0. But if there are no electrons in the subshell, we just don't include it. So its final electron configuration for lithium is just 1s2, 2s1. And if we count up the superscripts, the 1 and the 2, we get 3 electrons. And that's how many lithium has. So we're good to go. Now let's do some elements with a p subshell that actually holds electrons, unlike lithium, such as carbon. And carbon has 6 electrons since its atomic number is 6. And you can also count like 1, 2, 3, 4, 5, 6. Now, if we start counting from hydrogen, we can see that it has 2 electrons in its 1s shell, and 2 electrons in the 2s subshell, and finally 2 electrons in the 2p subshell. And since our 2p subshell isn't empty this time, we have to include it in the electron configuration, right? Unlike lithium. And so this gives us our final electron configuration of 1s2, 2s1, 2p2. And again, we can add together our superscripts to make sure we have 6 electrons, and we do. 2 plus 2 plus 2, 6. So we're good to go, and we can see that it works. Okay, so now let's try argon. And again, as before, we're going to start from the top left and go down to argon. And we see that our first S subshell is filled with 2 electrons. And then our 2S subshell is also filled with 2 electrons. Then our 2p subshell is filled with 6 electrons up here. And our 3s subshell is also filled with 2 electrons. And then finally, our 3p subshell is filled with 6 electrons. And if you remember, every element after neon up here has a d orbital or a d subshell. But we're not going to include an argon because we haven't actually gone through the d block yet. We've only been up here and we haven't gone down to the d block. So that's why we can leave it out of the electron configuration. There's nothing in it